Today I want to show you a very cool trick about spinning BLDC motors with microcontrollers. Now, this is for a very long time I didn't do anything fun, and this is very fun. Basically, what is this? It's very elegant piece of code to run the motors in very efficient way. So what we have here, we have a very powerful BLDC motor, and in here I have STM32 that is generating 3 phases, so A, B and C, shifted by the 120 degrees. And I have, of course, a very good encoder. It's basically 20,000 count encoder. It's really overkill. In reality, you should do that with back EMF, but because I have encoder, it's for me to make this code in 5 lines it's so easy. So why do I like this code? Because it can accommodate everything you throw at motor. So if you slow down, that's okay. Motors will slow down and nothing will lose the track or anything. And you can even spin it spinning backwards. Motor will always try to run. And if you want to make motor go faster, we increase the duty cycle of your PWM signal. So right now I'll increase by a bit, and it just goes. Yeah, again, it's very nice. Okay, so let's make it a little bit quieter. I will reduce the power. Okay, so how I did it and how much code do you have to have in order to run this? So I will shut down the focus and a bit defocus so you can read. Okay, so this is all there is to run this motor. So what I'm doing, I'm reading encoder from the register. It's timer count register. I am adjusting my encoder to my PWM lookup table, and I'm adding offset. This is why motor is spinning, because I have small offset between current position of the shaft and my magnetic field. So in this portion, I'm basically dealing with overfills and underfills. So basically, if I overflowing, because I'm using a lookup table, I can't simply have anything more than 4,995. Because it will generate me a hard fault. So basically, I'm starting from 0. So if you manage to make this code to 8 bits, you use char and or unsigned 8-bit, and it will overflow and underflow in hardware. So you don't have to deal with it. Same goes to 16-bit and 32-bit. And if you, of course, in FPGA, you can do basically any of this. So this is software just limiting. And last thing to do is to write to the PWM generators, so you can have free sinuses. And this is just adjusting power. So I mapped the current to 16-bit. So 16-bit 65535 is maximum power. That's it. That's all code to run the motor. It's incredible. If I write it to the 16-bit, it will run without these lines. So basically, you can spin the motor with 1, 2, 3, 4 lines of code. This is all you need to run the motor. This is incredible. I mean, I'm so excited for such a small amount of code, because I was running this motor in a synchronous way with very complex interrupts, calculation of the don't even ask. And it was rubbish. And this guy just spins without any problems. I can stop it. I can make it go faster. So let's go let's understand the theory behind this method, and we will and you will be able to write this code. So let's focus. Okay. Okay. So what I have encoder. So this is basically encoder going from 0 to 20,000, 20K. Okay. Now you need to have a map. Basically, you need to know how many sinus waves there is at one turn. For my motor, is 7 sinus wave means for a phase means one turn. So what I'm doing, I'm have a table with basically 7 sinuses that's capture compare. So we have to have seven sinus waves inside this lookup table. So this goes from 0 to 5,000. Okay. Now, and the trick is we divide encoder by 5. So basically, what we get a encoder that goes from 0 to 4,000. And now one turn of encoder means one turn of electric field. And what we do for the PWM registers, we add small offsets. I add like 220, and that's it. Motor spins, and you have to adjust this number for your encoder and your poles and everything else. Basically, is nothing more than like a distributor in very old car. When you turn your distributor, and it adjusts the firing. It's firing before top dead center or after top dead center, and I can show that to you. That's very cool. Okay, so what I'm going to do is increase the power a bit, quite a bit. Okay, so let's go to the autofocus, and if we rotate, this board is flexible. So if we basically bend it a bit, so it will go into shift my table automatically. You see, I'm applying just a little bit of pressure, and motor node changing and currents changing. So it's nothing more like a distributor. In one side it goes faster, in the other it goes quieter. How cool is that? So it's like mechanic. It's equivalent system of a car engine, where my duty cycle means fuel, and my firing order is controlled by basically an encoder position relative to the shaft. One side going to the, you see how it flex. So, and current is also changing. So if I go to the, I'm pulling toward me, it goes faster. And if I pushing, it goes slower, but the current decreases. So this is very cool. I mean, I'm so excited for such a small amount of code that works so well. And if we are trying to slow it down, it doesn't lose any of it. It doesn't lose track of a sinus table because it's mapped to encoder. Nothing can go wrong. Well, it can, and I already have some smoke because my tantalum capacitor just blow. I think because of overvoltage of back EMF or something like that. Okay, so thank you for watching. I'm very happy about this code. Yeah, I learned it from my boss at work. It was so simple and so effective. I at first I didn't believe, but yeah, it works. Of course, he do this code is running this code on FPGA, so he can do much better job than me. But in the few basically like 15 minutes, I made this work on the ARM from zero, from nothing. I mean, how cool is that? Okay, let's turn on, and I will show the encoder. So this is the encoder I'm using. Focus. Okay, so if you have any question or if you want to try it, I can help you. If you run STM, basically you just have to have some kind of encoder. It can be, it doesn't have to be very precise encoder. You can use Hall sensors and calculating angle from that, or any other method, but like back EMF. That's basically free lunch. But it's a bit harder because you have to turn off. Go to high Z and measure and calculate angle from that, and by calculating angle you will know where you have to be in the table of the sinus table or lookup table. So again, thank you for watching, and I hope you tried, because this is very cool and very easy and very satisfying piece of programming. So see you next time.